Okay, I want to finish off this discussion with the idea of a triple bond. And a triple bond will use the molecule ethyne to be the model here of a triple bond. So this is just a CC triple bond. It's as saturated as it can be if it's a triple, because carbon only makes 4 bonds, as you know. So 3 bonds are taken here, then that leaves 1 left over for hydrogen. So this molecule is CHCH, or C2H4 if you like. And we can imagine that each of the dashes here in this triple bond represent, respectively, the first one we can say is a sigma, and the other 2 are each pi bonds. So any triple bond is a composite of 1 sigma and 2 pi. So recall, a single bond is a sigma bond, a double bond is a sigma and a pi, and a triple bond is a sigma and 2 pi. So if we've watched our videos in order, we know that the sigma bond is going to be the direct overlap between my 2 hybrid orbitals. My one of the pi's will be an indirect overlap of a 2p and a 2p, so for example 2py and a 2py, and then the last pi will be an indirect overlap of the other 2 available p orbitals, which would have to be a 2pz and a 2pz. We only have 3 axes, x, y, z, so again the x is the axis, the bond axis, and the hybrid will take that one. My 2 leftover p's will be 1 in the y and 1 in the z, and this is why I can have 2 pi bonds of indirect overlap. So let's draw this out a bit. And again, let's start with the hybridization of that carbon, and like we did last time, let's, for example, talk about it in the margin. And I'm not sure if you can see it if I pull it down that much, so I will do this. Right, so carbon has the 2s and the 2p orbitals to hybridize, and the hybridization state here is sp. It is only sp because the triple bond is just counted once, and then the bonding pair to the hydrogen is counted. So I have effectively two electron groups to accommodate through hybrid. You can see why now, because we were really just counting the number of directional bonds. Yeah. So I need 2. I count the multiple bond once, and I have a hydrogen. So each carbon needs 2, so that's 1s and 1p. And they will hybridize 2 forms, keeping that number constant. If I use 1s and 1p, then I will get 2 orbitals, and each of them are called sp. Remember, in the name of the hybrid is its constitution, 1s and 1p, so there's always only 1s, but it's just sp. Okay? That leaves me 2 p's left over, which I will draw up here. Okay, so I have the 2 p's, and I have the py and the pz left over. So right away, I know that when my carbon atom hybridizes in this fashion, each carbon can make 2 sigmas and potentially 2 pi's. So you see just from the hybridization state what these atoms are capable of in terms of bonding if they are in this hybridization state. And so let's draw this out. So I have it's a linear arrangement, and so I have a carbon with an sp in this direction and an sp in this direction. Whoops, my camera just fell over. Let me fix that. Sorry about that. And the hydrogen is a 1s orbital, so there's my H. And there is my overlap for the sigma that is the carbon-hydrogen bond. And then I have the same thing with this carbon and a hydrogen on this side. And there's my sigma. And it's not a very good drawing, but, and there's my overlap between my two carbons. So there's a sigma there. So this is an sp on that carbon. This is the other sp on that carbon. And this is the 1s on this hydrogen. So I can see that this sigma bond is a direct overlap, so head-on, between the 1s orbital on the hydrogen and the sp hybrid orbital on the carbon. Okay, so it's this guy right here. And the same thing on that side of the molecule, it's symmetrical. Now, the sigma part of the triple is right here. It is the head-on part. It is an overlap, a direct overlap between an sp hybrid orbital on carbon number 1 with an sp hybrid orbital on carbon number 2. So again, this carbon number 2 has two sp hybrid orbitals, and one of them overlaps with a 1s on hydrogen to form this sigma, this bond, and the other here. So going back to my hybridization state, remember it used an s and a p to form two sp hybrid orbitals, which left two p orbitals left over. And p's do not make sigma bonds, they make pi. And so these two leftover p's, I'm going to draw one in red. So if this is the x-axis, let's draw this one in this direction. So remember, a p orbital has two lobes, and the hybrid orbital only has one major lobe. So while that hybrid orbital looks like one figure 8, it's actually not. It is, this hybrid orbital is one on its own, and that's another one. Whereas when I draw a p orbital, this is one orbital, and this is my 2py. And it's the 2py because this is carbon, okay? And carbon's valence electron configuration is in that second row too. And this carbon also has a 2py. So I see that the indirect overlap, let's draw them kind of like antennae talking to each other. There's, it looks like two places, but it is, I guess, two locations here of overlap, but these together constitute just one pi bond, okay? So one pi bond has an indirect overlap, say, above and below the bond axes. So this pi bond is an indirect overlap between the 2py on carbon number 1 and the 2py on carbon number 2. I have to match the letters, otherwise they wouldn't align to interact. But in this example, I have a third. I have a triple bond. And this is as big as it gets, of course. So now this p orbital is the pz. So I'm going to try and make an orthogonal representation here between the x and the y and the z. So I'm going to use this right here, this angle. So there's my 2pz on this guy, and I'll draw it in the same orientation. There's my 2pz. Looks like a 2, but it's a z. 2pz on this one. And so I have now overlap here. It's going to look a little messy, but anyway, above and below the bond axis, but in the z orientation. Okay, so let's write this out, and then it will be complete. So my triple bond, is, it's a one part sigma, so a sigma direct overlap between So I'm talking about the triple bond, the CC triple bond, okay? So I'm talking about this sigma and not the sigma between the C and the H. So I'm going to fully describe the triple bond. I'm starting with the sigma component, which is a direct overlap between, think about it now, what is there a direct overlap between on these two carbons? The two carbons are hybridized. The hybrid orbitals are used not only to bond the C to the H, but the C's to each other. Right, so it's a direct overlap between sp hybrid orbital on carbon number 1 and the sp hybrid orbital on carbon number 2. So if you want, we'll label them carbon 1 and carbon 2. Now the first pi bond, we can do them the Z first or the Y first, but let's just follow convention. We'll do the Y first. This is an indirect. So that first word is really very important. So sigma direct, pi indirect. And it's an indirect overlap between, it's always between because it's always between two players. Indirect overlap between, so match up the letters, 2py, it's 2 because it's carbon, and if we go lower in the periodic table, let me grab the periodic table, if we were doing, for example, if we were talking about phosphorus, it would be a 3, an n equals 3 level, or for sulfur it would be an n equals 3 level p orbital, but I'm up in carbon, so I'm just second row, and that's why it's at 2. So a 2py on carbon number 1 and a 2py on carbon number 2. All right, so yeah, I was thinking about this when I had the table here. So you might be thinking, well, what if carbon was making a bond with sulfur? Yeah, you'd still want to match up your letters Y with Y, but it might be a 2py with a 3py. But it's the orientation that's important. And finally, the second pi bond, as soon as we see pi, we know it's indirect, and we also know that it's made up of p's and not hybrids. So indirect overlap. I'm writing around the camera here, so that's why my writing is not very neat, because I'm holding the pen awkwardly. Pi is an indirect overlap between, again it's a 2, but this time pz on carbon number 1 and a 2pz on carbon number 2. So it looks a little bit complicated, but you should be very impressed if you can reproduce this, if you can follow along, understand it. I think, and I'm sure you can, and I'm confident that you are, that you have learned hybridization, or you've gone back to view the slides or the videos to refresh. And we're looking at a condensed molecular formula. We remind ourselves of the way the hybrid orbitals are formed, and if some p's are left over, and now we find use for them, p's in the pi. And you can make use of your attempt at a three-dimensional sketch here, rough as it is, to rationalize where the indirect overlaps are versus the direct overlap. But this is very important for you to be able to describe, okay? And I'm sure you'll be asked to produce that description. So we have done, in summary, these 3 videos. The sigma, the single, double, and triple bonds using just straightforward CC bonds. But you need to take this, understand it, and now apply it to the other scenarios, these larger molecules. And I'll do one with you in a 4th and final video here to post for practice. And that should bridge your gap into general chemistry too.